B10. So B10, right, is just more of um, a problem that kind of stretches your understanding of what's happening and when we're talking about concentrations of H plus and OH minus, right, in water for pH. And really understanding what's going on, right, but applying those same concepts to now a new system in these cases. And so another molecule, right, that can undergo autoionization similar to what water does is ammonia, right? And so if we look at ammonia, right, we have it's NH3, right, and it's straight up liquid and everything like that. You can imagine, right, because it has 3 hydrogens, that it could undergo, and it has a lone pair, that it could undergo autoionization where one of the ammonias donates one of its protons, one of its hydrogen atoms over to a different one, and then forms NH4 plus, right? So ammonium, but then it also forms NH2 minus, right? So the amide. Right. And so if we write this out, right, and it's very similar to what we have for water, right? So right, so we have NH4 plus, right, and this is going to be dissolved now in ammonia, right? So I'm going to write it as AM rather than as AQ, right, for aqueous. And then you also have, right, NH2 minus in those cases, right? So very similar. So if I were to just simply map on what we know about water, right, we have for water, right, we have H2O, 2 of these, and it forms H3O plus aqueous plus OH minus aqueous, right? So again, right, extremely similar, right? It's basically the same type of reaction where you have 2 of the same molecules, and one of them acts as a base, one of them acts as an acid, and they both donate, and right, and then they undergo the acid base reaction, and you form the dissociated version of them, right? So the autoionized version of them, and stuff. So you can expect that to be possible in ammonia. And so the next part, right, is it says to draw the Lewis structures of the acid and the base formed, right? So we should be able to do that. So if we go and do that, right? So for NH4, right, we have nitrogen, right? It's NH4 plus, and so we're gonna have 4 hydrogens bound to it. Right? And then we have the formal positive charge on the ammonium ion in that case. And then in the case, right, of NH2, right, so you have your nitrogen that has 2 bonds of hydrogens, right, and then you have 2 lone pairs combined on there, right, and you have then a formal negative charge on the nitrogen in that case, right, because it has 1 extra electron to meet the octet rule, right. So those are what the Lewis structures are there, right. So, and again, right, that's very similar to what we have for water, right? Because in the case of water, right, for H3O plus, what we have is, right, this species right here where we have 3 hydrogens attached to the oxygen and 1 lone pair. In that case, right, the oxygen meets the octet rule. And then in the case of the OH, right, you have the oxygen and the hydrogen bound, and then you have 3 lone pairs around the oxygen. Right, and that then has a formal negative charge, right? So again, very similar of what's happening between the 2 of them. Right, and so the next thing is, right, give the equilibrium expression for the autoionization of ammonia, right? So looking at it, we know that liquids aren't part of the equilibrium expressions, right? But we do have like things that are dissolved in those solutions, right? That are dissolved in liquids. Are part of the equilibrium expression, right? And so for anything that's water-based, it's always everything that's aqueous. But if you have things that are dissolved in ammonia, right, those are going to be then the things that you have right there. What does the AM subscript in part A mean exactly? It just means that it's dissolved in ammonia, right? So it's not, so, right, so like L is liquid, S is solid, G is gas, right? And then if you have things that are dissolved in water, right, you refer to them as being in the aqueous layer, right? And so the AM stands for that those are dissolved in the ammonia layer, right? That they're dissolved in the ammonia. They're not a liquid, right? They're not a pure liquid, they're not a pure solid, and they're not a pure gas, right? They're just simply ions dissolved in another solution in those cases. And so the typical thing that you encounter, especially early on, right, is everything simply gets dissolved in water. But if you were like to make, but you can also make solutions in methanol, right? And so in those cases, right, you would then have as the subscript, right, CH3OH to like signify right, that something is dissolved in the methanol, right? If you were to have something dissolved in like benzene or something like that, right, then you would usually have like benzene or something like that be the subscript to signify that your reaction, those different ions or even like the different molecules, right? Because it doesn't have to just simply be ions that dissolve in things, are dissolved into those layers. In those cases, right? And so that's what I'm signifying there with the AM is saying that the NH4 plus and the NH2 minus is dissolved in the ammonia layer. Right. And so that, I mean, it's just the same thing as, right, if I were to write AQ, right, that's just simply saying that it's dissolved in the aqueous layer, right, which is the water layer, in those cases. And so, and that helps, right, you identify when you are talking about the equilibrium expression, right, and you're looking at, what the autoionization of ammonia is, right, that has to then be the concentration of the NH4 plus, right, because that's one of the dissolved species, and then also the NH2 minus, right, because that's the other dissolved species. And the ammonia, because it's a pure liquid, isn't going to be part of the the equilibrium expression, right, because it has an activity of 1, so it's not going to contribute, right, because it's a pure liquid in that case, right. Whereas in the case of the ammonium and the NH2 minus, right, both of those are dissolved in the ammonia, and that's how they carry over, right? And that's the same thing that happens for water, right? So if you have, the autoionization of water, what you have there, right, is you have H3O plus and OH minus, right? So those concentrations are what matter there, right? And so, and we know that that value, right, is 1 times 10 to the negative 14, right? That's what that equilibrium expression is. And in the case of the KAM, right, I give it up here, right, so that's 2 times 10 to the negative 29 in those cases, right? So again, very similar, right? It's basically the same thing, just, kind of stretching, the understanding a little bit. But that's what the AM means, right? It's just simply signifying that those ions are dissolved, right? They're not, in their pure state, so to say. Because you can have, so there are things called like ionic liquids where you have, essentially salts that are, ionic salts that are melted to the point where they are liquids. And then those become the solutions that the reactions happen in and stuff like that. So in those cases, right, again, you have to then think about, so like sodium chloride, right, there's, sodium chloride melts that can be used for reactions. If in those cases, right, like if other things are dissolved into that melt, even though based off of, what we think about at this level, right, the sodium chloride, you'd be like, oh, well, that has to be part of the equilibrium expression or whatever, right? But it's not, because it's just probably going to be like the solution if, especially if it's not participating in the reaction or anything like that. Right. If it's just simply the solvent, so to say, that the reaction happens in, right? And that's what's happening here, right? Is that the reaction's happening in pure ammonia. And so, ammonia should be the subscript in that case, right, to signify that's what it's being dissolved in. And then D, right, determine the concentrations of the acid and base in ammonia, right? So we just do the same thing that we would do in any other, scenario, especially, like, thinking back to how we would approach solubility, where what we can do is we can just simply have, excuse me, I feel like I need to get some water, but I'm good. Right, where we have KAM, right, the equilibrium constant of the ammonia, right? Since we know that the concentrations of the ammonium and the NH2, they're going to have to be equal to each other, right? We can just set both of them equal to X, right? So you can have, right, X times X is equal to X squared, and that's going to be equal to 2 times 10 to the negative 29. And so from there, right, all we have to do is just simply take the square root of the equilibrium expression. 2 times 10 to the negative 29. So what we get is, X is equal to 4.47 times 10 to the negative 15, right? And that's going to be the concentration of NH4 plus, right, at neutral pH in ammonia, right? And also the concentration of NH2 minus in this case, right? Which 4.47, yep. And so it matches there, right? And that's the same thing that we do with water, right? So if we take water, right, if we take KW in this case, again, right, H3O plus and OH minus, They both can be, you can just throw an X, right? Because those concentrations should be exactly the same for the autoionization. So you again have X squared, and this is going to be equal to 1 times 10 to the negative 14. And so now if you take the square root of that, what you get is 1 times 10 to the negative 7, right? And so that's the the concentration of H3O plus and OH minus. Oh. In those cases, right? Which makes sense, right? Especially when we're thinking about pH, right? Because a pH of that relates to the concentration, right, of a pH of 7, right, which is a neutral pH, would be where you have a concentration of 1 times 10 to the negative 7 H3O plus in solution. So that's the relationship right there. And so again, right, and then for part E, it's just simply, right, determine the pH of pure ammonia at 25 degrees Celsius. So again, all we have to do is just simply take the negative log of the concentration of the acid species of what we're looking at, right? And so, in water, that's H3O plus. In the case of ammonia, right, that would be the concentration of NH4 plus in this scenario. So if we were to look at the pH in this scenario, right, so this would become, right, if we're, I'll stick with blue, pH, right, is equal to the negative log of H3O plus, right? So this is for the water scenario, right? And so in this case, right, negative log of 1 times 10 to the negative 7, right? You plug that in, negative log of 1 times 10 to the negative 7. What do you get? 7, right? And so that's, that's neutral pH, right? Pure water, right, would have that pH right there because of the autoionization of water. And so if we do that same exact process for ammonia, right, what we have is pH is equal to the negative log. And so in this case, right, the species that's similar, right, is going to be the NH4 plus now. And so we plug those values in, right? So negative log of 4.47 times 10 to the negative 15. Right? What we get is negative log of 4.47 times 10 to the negative 15 is 14.3. 14.4, yeah. I mean, it's probably a rounding error or difference in those cases, right? And so that's what neutral pH for ammonia is, right? Is a pH of 14.3, right? Because that's all pH is just simply the concentration of the protonated solvents species, right? That you have in those cases, right? And so, for water, it's H3O plus, and so that's what we typically associate that with, and that's 7. But in the case of ammonia, right, when you do the autoionization, when it undergoes autoionization, even though, right, times 10 to the negative 29, a very small amount of that is going to happen, right? That very much does not favor product formation. Right, what you get is, a really high pH because you have very, very few of the, acid and base, present, so to say, right? But you can go through, right, and you can do a very similar problem, right, where I can be like, oh, I'm going to dissolve in pure ammonia, these other species, right? And then you could, figure out what the Kas are in ammonia, right? And so when you go into orgo, that's going to become very important because a lot of organic reactions do not happen in water, but you still have to understand what, pKas are and how pKas can actually change and shift if you're in different solvents, right? If you're doing a reaction in methanol, right, it's going to be different, like different pKa values for certain species compared to if you're doing it in DMSO, or if you're doing it in water, if you're doing it in other solvents and stuff like that. And so a lot of those things kind of come back, right? And so you have to think about the fact, right, that there's more to what's going on than just simply the surface level, right? And that might help. I don't know, right? I mean, this is I like this problem, right, because it kind of like forces you to like think outside of your typical thing, but it still like maps perfectly with what you've probably already been like learned about autoionization of water and where pH and all that stuff comes from, personally. So it's a if you understand what's actually happening and why we have all those different values for water, right, you can then figure that same stuff out for for other solvents, right, that can autoionize. So cool. But that's B10.